Thank you very much for being there today. I'm really glad to be here. And the outline of the presentation is the following. First of all, I'm going to provide a limited view of 5G. Second, I'm going to talk about the challenges that we treat in our group, some of the challenges that we have treated in our group, and they are related to performance, reliability, and sustainability. And finally, conclusions. So first, let's start with the overview. You may wonder what is the difference of 5G with respect to the previous technologies. And there are many technological differences, but there is something that is fundamental, is that 5G was done considering three large classes of traffic. The first type was the enhanced mobile broadband. And for enhanced mobile broadband, we need a lot of throughput, so a lot of capacity. So an example of applications that are within the class enhanced mobile broadband are augmented and virtual reality. Next, we have the ultra reliable and low latency communications. And those are the communications that need a very, very, very short latency. For instance, connected cars, mission critical situation, industrial automation, etc. And finally, we have the massive machine type communications, such as connected IoT sensors, smartwatches, smart meters, and so on. So the organism that put in place the requirements for 5G, that is called the International Teletraffic Union, they defined 8 KPIs, so 8 key performance index to be considered for the 5G applications. Among those 8 KPIs, we consider that the most important, in my view, the most important are latency, throughput, and large-scale coverage. And now I'm going to explain each one of them. Well, this is a slide on latency. And in 400, you have milliseconds over here and applications over here. So imagine that you are blinking your eyes. How long it takes you to blink your eyes? And it takes you around 400 milliseconds. Now, if you need to talk over IP, you can, the voice, the packet that travels from the origin to the destination cannot take more than 200 milliseconds. If it takes more than 200 milliseconds, your voice is going to be heard in very, very badly. Now, if we go down to 100 milliseconds, we have the maximum warning if you are doing a vehicle to infrastructure application. You cannot go beyond 100 milliseconds in time of the packet to do the warning. And if we are talking about vehicle-to-vehicle pre-crashing information, then we are talking about 20 milliseconds. Now, let's talk about virtual reality and haptic communications. So virtual reality, well, we all know what it is, but virtual reality requires very, very low latency because your brain has to get accustomed to the virtual reality. So the latency for virtual reality must not be higher than 7 milliseconds. And if we are talking about haptic communications, which are the communications of the tactile communications, are the feeling of, you want to transmit your feelings through the internet, for instance, you have to go beyond 1 millisecond. So this is, you can see that from the blinking of the eye, which is 400 milliseconds, down to 1 millisecond. Now, the problem with latency is that latency has several components. You have the treatment delay, you have the transmission delay, you have a queuing delay, so a congestion delay, and finally, you have a propagation delay that is the speed of light delay. So 5G is very efficient in terms of treatment and transmission delay. So it's a protocol, it's a set of protocols that were set to be very efficient for those. Now, the problem is the queuing delay and the propagation delay. And to reduce the maximum, the propagation delay, what has been thought of is to add what is called the edge computing and to do a disaggregation of the functionalities of 5G that was put in place. I'm going to show a little bit later on what this is about. Now let's talk about throughput. So throughput is the capacity that you require for a particular application. So let's say that the application is 360-degree virtual reality. Well, for low resolution, you need at least 25 megabits per second. For a resolution that is like HD TV, you need between 80 and 100 megabits per second. And if you want to have a resolution of 4K, then you need 600 megabits per second. And to put you in perspective what this means, I have here the Netflix values. So for low resolution Netflix, you need 3 megabits per second, HD TV 5 megabits per second, and 4K 25 megabits per second. In terms of technology here, well, we have the 4G and the 5G. These are the values of throughput, absolute theoretical values. So you cannot, this is the values that you get when the world is perfect. You are the only one in the network. There is nothing else. So essentially, you never get those values for the uplink and for the downlink. So what we're seeing here is the 4G technology. The maximum theoretical throughput in the downlink is 300 megabits per second. So we cannot do a virtual reality with 4G. With 5G, we might be able to do it because it goes up to 10 gigabits per second theoretically. So this gives you a flavor that we had first latency and now we have throughput. Now I'm going to talk about the third KPI that for me is very important, which is coverage. So coverage is a necessary but not sufficient. So people that work in mathematics, they understand what is necessary but not sufficient condition for user equipment to be able to access the network. And what is important is that we need large-scale coverage for distributed IoT applications. We have, because we are going to have applications in which, for instance, you are going to have a sensor in a cave, and you have to be able to cover even that cave. So we are talking about very, very large distributed applications. Now, the problem with coverage is that coverage is related to throughput and related to frequency, and in a way that is not always what we would like to. So we have higher frequencies, they produce more throughput, and more throughput produce less coverage. So if you want to have higher frequencies because you need a lot of throughput, that's okay, you're going to have your throughput, but you are going to get less coverage. So in order to do that, what 5G did, the people that were putting together 5G, they defined the frequency that was going to be used with the technology in two large levels of frequencies. There is a level which is beyond the 6 gigahertz. So just to give you an idea, Wi-Fi, the maximum Wi-Fi that you have at home is 5 gigahertz. So it's below 6 gigahertz. This is what is called the FR1 level. And then you have the level that is above 24.6 gigahertz, though this is what is called the FR2 or the millimeter wave level. And this is unique in the telecommunication technology. We don't have any other technology that has these two ranges, very, very distinct and different ranges of frequencies for the same technology. So some notes about coverage. If we take a macro base station, so a base station of the FR1 type, the coverage of that macro base station can go up to 2.5 kilometers, whereas a typical range of coverage for an FR2 base station is between 100 and 500 meters. So what this means? It means that FR2 covers 1/5 of what is covered by FR1. So this means that for the same we need the same area, we need 25 more small FR2 base stations. to cover exactly the same area that we covered before with the macro base stations. So it's a huge proliferation of small base stations. Now, what are the implications of this type of coverage? So in order to show you the implications, I'm going to show you what is being thought of as the 5G evolution. So this is a typical macro cell site, a macro base station, in which we have the antennas, we have the radio unit, we have the BBU, which it is the baseband unit that does the signal processing, has some RF equipment that deals with the network access. And between the antenna and the BBU, they are usually co-located. And there is just a small fiber cable in between the two. And then you have a router that takes the signal and sends it through what is called the backhaul. That is usually a fiber backhaul. And the signal goes to the mobile core where some functions take place. So this is the typical RAN. Now, imagine that you are going to replicate that typical RAN for, instead of one base station, you're going to replicate it for 25 cells. So of course you cannot do that. So the first implication of this situation, of this small cell situation, is that it's cost. So it's just too costly to have a backhaul fiber for each individual cell. You cannot have that. So what are we going to, what did they do with respect to that? Okay, so here things get excited and complicated. So the first thing they did was they say, okay, in that case, let's split the functionalities of the antenna and the base station. So we split the functionalities. We are going to have very dumb antennas, and we are going to put the intelligence that was before in the base station, collocated with the antenna. We're going to put it in two places. Some of the functionalities are going to be very close in what is called the virtual distributed unit, and other functionalities are going to be put a little bit farther away, which is called the virtual centralized unit. It's a central hub site. So, and now with this splitting of functionalities, now we have two different elements in the architecture of the network. We have the front haul and we have the mid haul. Before we just had the back haul. So what is the implication of this? So the implication is that all of a sudden we have congestion in the front haul, because we had this, it's not just one antenna, we may have several antennas in the front haul. So there is the necessity of several signals that are going through the same network. So there is congestion in the front haul, whereas before we didn't have that. And we need to further reduce the propagation and the network latency, because before we had everything that was done very, very close to the antenna. Now we have this open mid-haul that has some latency that is added. So we need to reduce that latency. So how this is done? Here is what I wanted to show you. And this is the evolv 5G architecture. So we came from the antenna that I show you, just with the BBU and the backhaul, to this type of proposal. So what there is here, we have the edge that has been added, and we have a bunch of antennas that communicate with that edge, and we are going to have virtualization everywhere. So essentially, whatever function you have in the network is going to be virtualized. So what this means is that there are going to be a lot of data centers, because there is virtualization in the edge, there is virtualization in the core, and there are going to be also a lot of antennas in the network. So there are, therefore, this evolution, which is very good for some applications, because you need that flexibility to be able to go down to the 1 millisecond latency. So this is needed if we want to have this type of applications. But at the same time, this type of flexibility creates reliability and sustainability problems. Why? Because complexity increases the probability of failures. And there is a large increase in the number of the data centers, and the data centers are really power hungry. So data centers are really a problem in terms of sustainability. And of course, we have a large increase in the number of cells, which will also have an impact both in reliability and in the sustainability of the system. So now I have finished the overview of the 5G. I'm just going to go through some of the issues that I consider are challenges for the system in 5G and beyond. And the first one is performance. So when a user in a normal network, like a normal cellular network, when a user sees a degraded network performance, well, the user is going to call the operator. It's just going to say, well, there is a problem here, please do something. But what about if there is a malfunction of a performance degradation on one among tens of thousands of sensors and actuators? For example, in a smart city, in an automation system, in a very largely distributed setting. So how can a device call the operator and say, there is a problem here? Or how can the operator realize that there is a problem there? So this, this is what the problem that we had when we were facing, well, the performance of smart cities. I mean, how can you evaluate the performance of these very largely distributed systems? And we picked up the name machine experience, which is in respect to what we call, for humans, we call quality of experience. So quality of experience is the experience that you have when you're facing an application. Are you seeing your application as you wish you see it? And a machine experience is the equivalent, but for the application that overall the application. For instance, if we are having an automatic system, is this automatic system working as it is? So the challenges we had is that many applications are largely distributed. They are citywide distributed. We have tens of thousands of devices. So we don't just have a few devices, but tens of thousands of devices. We have hundreds of base stations. So just the city of Montreal, and we are talking just macro base stations. No, so we're not talking about micro base stations. Macro base stations, we have around 500 per provider. There was no data because the systems were not deployed. And even if they were deployed, well, operators, they don't always want to give you data. And the other problem was that current simulators are only able to evaluate local problems with just one or two base stations and just a few devices. So the idea of this largely distributed application, we couldn't do anything about it. So what we did was, and I'm going to share my screen, we created the simulator. So we said, okay, we don't have data, we don't have what it requires, but let's see if we can create our own simulator and do what we want to do. So we went around trying to find data, and we found data for the city of Montreal, for the city of Toronto, and for the city of Ottawa about the location of elements in the city. So you have here, for instance, the machine types. We have, if you want to know the parking spots, well, that you have, well, here we have the parking spots. You can do a zoom in, and well, you can zoom in even more here, and then you end up knowing a little bit more, and you end up knowing where the parking spots are in the city of Montreal. And the same can be said about the, let me reduce it, okay. About, for instance, the traffic signs, where are the houses, where are the traffic lights, and so on. So what we did is that we assume that all those elements that are fixed in the city would have sensors and actuators and would produce traffic in terms of telecommunication traffic. And we are able to change the stochastic characteristics of that traffic. So say what are the arrival of packets, you know, what is, whether it's Poisson or it's another type of arrival, the length of the packets changes as well. So we are able to produce a lot of traffic just knowing the location of the elements. Of course, those elements, they must be around a base station. So fortunately, in Canada, we have the possibility of knowing where the base stations are. So we know where the base stations are in the city of Montreal for each one of the providers. So you have where the base stations are located. And we know also the characteristics of the base station. So what is the capacity of the base station? And from that information, we are able to run some programs for to know what is the propagation around a base station. So we have, you see here, this type of circles. They are the results of the propagation, a propagation study around the city of Montreal that we made. Now, usually what we do is that we define an application that is composed of the different types of machines that I presented. We try to, we define what type of traffic we are going to put for every application, and then we run the simulation. But this takes time to do it online. So we have some demo simulations here in which you can show, we can show the results of the simulation. So we do the simulation and we consider different types of KPIs. In this case, this is the total traffic, but we could have something different. For instance, the total number of created packets is the same, or we could have the total rack attempts is the same. Let's see something that is different. Maximum connected UEs. Okay, there are no, this doesn't work today. Okay, the total traffic here. Okay, so the total traffic, what can you do? You can go in and you can get information about the results that you obtain from the simulation. You can get also the antennas that you have in this place, and you can also see the graph of what is going on in the simulation. So in the graph of the simulation, you say, let's stay with the total traffic, and we can see how the simulation, the value changes all over the time that we consider in the simulation. So what do we do with this? What we do with this is, let's go to the presentation of to this presentation. What we do with this is obtain data. So this, we do it essentially to obtain data. And once we obtain data, we try to be able to determine whether an application, for instance, is behaving as it should, whether there is a base station that is behaving as it should. What if we also know of what if we add, because we also have the possibility of adding elements to the application. For instance, we can add a base station in a particular location. So what if we add this base station, how things change with respect to the application and so on. So I just had these slides in case things didn't work. And so what challenges do we still have? We have huge challenges to continue developing this framework. First of all, the challenge of computational complexity. And what is, I didn't tell you, but with 5G, we are simulating at the millisecond level. So it's with 4G, we're simulating at the millisecond level. And with 5G, we simulate either at the millisecond level or below the millisecond level. With 5G, you are able to even work at below the millisecond level. So one question we may ask is if statistical approximation for simulation are rich enough to capture 5G performance, because we need to do something. We cannot simulate this huge network at the millisecond level and have applications that last, for instance, half an hour. You know, this is huge in terms of simulation. So we have to approximate but the question remains if, and we are actively working on that, the question remains whether this can be substituted by some approximations. The second problem is the parallel and distributed computing. And what happens is in this framework, we have systems that can be, for instance, the transportation system, or can be, well, the electric system. So you have systems that are going to rely on the 5G infrastructure. So you have these two systems that go together. Now, the linking the two systems together is not easy in terms of simulation, among other things, because we have to do parallel computing for the simulation to be at least quicker. And for instance, if you have mobility, well, the car is going to go through one base station and then to another base station and then to another base station. So you have a linking between what happens in a base station with respect to what happens in the other base stations. And if you send everything in parallel, you'll have to do synchronization of your parallel threads, which is not straightforward to do, and without slowing the simulation. So we need methods for implementation of these kind of things. And finally, with respect to the computational complexity, well, it would be very nice for the operators to have this type of tools, but for real-time decision making. So if you have, for instance, a dispatching system, and you want to know how this is going to work in a 5G system, well, to have this type of tool would be nice, but we need to overcome the computational complexity. The other problems we have are in terms of modeling, and this is very important because what is, for the time being, what we have modeled is just the access, and we consider that the core behaves in a certain way, and we add some parameters for the core. But in reality, we should encompass the data center and the access nature in this type of simulation. And they are two different animals. So you have the VMs on the one side, and you have the radio blocks on the other side. And so how do we can model effectively these two elements that are going to be put together? And finally, the question of cross data. Can data from systems relying on 5G can be used to try to have a quicker simulation? So these are the challenges that we still have for this framework, and the 5G performance challenges are huge. So there is a lot of work to do in that respect. Next, let's go to the next challenge, which is reliability. And I'm just going to present a very simple problem in which we used some data from the simulator. So I'm presenting here the sleeping cell problem. So essentially what happens is that we have many cells. As I said, the city of Montreal may have like, for an operator may have like 500 cells, around 500 cells. And it's very difficult to be monitoring in real time what is happening to every cell. So operators just rely on users that call them, and this is not working, then they go there and realize 3 days later that the cell is sleeping. This is what we call the sleeping cell problem. Of course, when we are going to go through 5G, this is going to be more critical because we are going to have more cells and smaller cells. And be able to say, well, there is a cell that has a problem is a real challenge. So the question that we had is, can we detect there is a cell just using aggregated data? So we have traffic data, which is aggregated data. In our case, we produce the data from the simulator, but the operator may have the aggregated data itself. And can we use that data to say, well, this cell is not working? So let's see. So we had the first idea was to have the geographical area of the city is divided in what we call the grid points, which are not, it's not a very good name because it's not a grid point, are just grid squares, you know, little squares. And these little squares, we can decide how big or how little they are. when we do our propagation, well, we say that everybody that is in that little square has exactly the same power, exactly from the same antennas. So this allows us to be able to manage what happens at the propagation level, because otherwise we need to know exactly in each geographical point what happens, which is almost impossible. So we have these squares, and in each square, as I said, there are different antennas that can that can cover that little square, and we have what we call the priority list. So the priority list gives us the priority of the antennas that are from which the devices that are in those places are going to take the power. So for instance, here is antenna A, antenna B. In this square is going to be antenna A, next antenna B, and next antenna C, and so on. So it means that if antenna A, in this case, antenna A fails, then antenna B is going to take over. And if antenna B and A fails, then antenna C is going to take over. So this is the way we have in our system, and more or less is the way that operators have this information. The next idea is the idea of proximity range. So proximity range is when you have this priority list, if two antennas are in the same priority list, then they have a proximity range. And depending on in which place they are located in this priority list, the proximity range is going to be, for instance, here A and B are 1-2 proximity range, A and C are 1-3 proximity range, B and C are 2-3 proximity range. So I have here the examples, more detailed examples of what this proximity range means. Now, the next idea is to take this proximity range into a neighborhood of cells. So what we have is, this is the cell and the study, and then we have the 1-2 proximity range that we call it the neighborhood category 1. And then the 1-3 cells, and we call that the neighborhood category 2, and so on. So we have a set of neighborhoods around the cell that might be failing, of base stations that have antennas that are going to take over when this cell goes down. Now you may wonder, why do we need this notion of neighborhood when we have the notion of distance? So we have here, we could have used distance. We say, okay, what is the antenna that is the closest to this place? And what is the second closest, and so on. And in fact, we did that before. Our previous study was with Voronoi, and we did that before. But the problem is that propagation is nonlinear. So you may have situations in which you have an immediate base station, which is not the one that is going to cover best. Maybe, for instance, this base station, in this case, gives more power to this area than this base station, which is very close. So this idea of neighborhood categories is really important. So we did a machine learning problem, very simple binary classification problem, and in which we have a vector of statistics of different KPIs. So the bunch of KPIs that I show you, like the rack attempts, the total traffic, the mean throughput, etc., etc. So we had a bunch of KPIs that were aggregated over bins of time. And that was very important for us. The fact that if we could detect things with aggregated values. And those KPIs were computed for the cell and the study. And then we concatenated to that vector the statistic for all the cells that belong to a neighborhood N. And the target was reached if a concatenated vector belonged to a failed cell. We had different time intervals and neighborhoods that were considered, and the AUC and the false positive rate using popular classifiers were compiled. So here what we have is the average AUC scores obtained with extra trees, which was the best classifier that we got. And in here, we made tests with different neighborhood categories. So the 1, 2, 1, 3, 1, 4, and so on. So we included those neighborhood categories and aggregations of the statistics in 5 minutes, in 10 minutes, in 15 minutes, and in 30 minutes. And what is interesting is that even in 15 minutes, we got the best results with the aggregation in 15 minutes. Which is good, which is excellent, because it means that even if you have a phenomenon that is working in the millisecond level, well, if you aggregate in the 15 minutes, you are still able to say something if you do the modeling correctly. So let's go to the next challenge, which is sustainability. So what happens with 5G is that 5G is much more energy efficient in terms of watts per bit than 4G or 3G or all the other generations. However, because there is a very large increase in demand, the base station that covers the same area is more than 68 more energy hungry because of the demand that is expected in that area. So this is without considering the fact that for the FR2, so for the higher frequency, we will have this 25 per area more small cells that are going to be added to this. And the huge data center increase, number of data centers that we are going to have in 5G. And data centers are really a problem. I mean, data centers have really a sustainability problem. Moreover, if brown energy is used, well, look at this table. You go from hydro and through coal, for instance. So you have 100 times more CO2 emissions. Just to give you an idea, China, which is a very important country in terms of consumption and in terms of deployment of 5G, well, in China, there is 2.5 million mobile towers that have to be updated to 5G. And this update will take them beyond 100 terawatt hours of consumption and 27 billions of kilos of CO2 per year. And I have here the curve of the energy consumption of China Mobile, which is one of the major China operators. And you can see that increases over time. This is terawatt hours with respect to year, increases over time. And then between 2019 and 2020, there is a steep increase. And no wonder, because in 2019, 5G was implemented in this company. So we can see that there is going to be a larger increase in the years to come. And to give you an idea of how much these terawatt hours mean, I have here the Hydro-Quebec exports for 2020, which is around 33 or 34 kilowatt hours. So this is tending towards the total exports of Hydro-Quebec for 1 year. And this is just for one operator in China. Okay, so in order to counter this problem, we had what I feel is a very effective modeling idea. It's a simple but effective modeling idea. So the idea is the following. Imagine that you have 3 base stations. And these 3 base stations, here we have what we call the test points. So it's aggregated points of demand. And usually suppose that this is the high demand time of the day. And then in the low demand time of the day, you have fewer points of demand that are active. So you can just put down 1 base station. So this is mostly what everybody did when the sustainability problem became very important in ITC. This is the type of modeling people were doing. Say, okay, let's put down some elements and see what happens. Now, what I say, it's a simple but very effective idea is the following. If instead of having 3 base stations, we had planned for 4 base stations in an intelligent way, of course, it's not in any way, but in an intelligent way, we could put down 3 base stations during the operation. So we could have huge savings just by adding a small base station. So we use that idea in the planning of cellular networks, and we had incredible results. Essentially, what we do is we give slack. So what we're doing is at the planning stages, we're giving slack to the planning so that the operation is going to be more energy efficient. And in some results, what we did in terms of modeling is that we take an objective function that takes into account the capex, so the classical planning capex, versus the energy efficient OPEX. And for this, we assume that there is like a typical day in which the operation is going to follow the demand. And we incorporate that operation into the constraints of the model. And we do this trade-off between the CAPEX and the OPEX. And we end up having, for instance, with just 10% increase in CAPEX, sometimes we got 70% reduction in OPEX, which is huge. So we push the idea to include solar equipment, because of course what we did was just put down base stations, assuming that the technology allows us to put down completely a base station. Now, what if we have, when we are doing the planning, base stations that are solar? How the planning ends up and how this changes in terms of sustainability. So we went through the literature, and there were some works that touched the solar energy in cellular systems, but they all consider that solar doesn't cost anything. That you put solar and it's wonderful and everything is going to work like that. And in general, they just look at the solar operation, how to operate the system. Nobody consider long-term planning, assuming that there is solar in the network. So we had a very detailed and realistic cost of all the equipment that is involved in the planning. So we assume that there are the solar panels, then there is a charge controller, there is the battery, there is an inverter, and we have this energy, the energy to feed the antenna transmission power can come from the solar or can come from the grid power. And depending on the availability and the the charge of the battery, well, we go from the battery power or we go from the grid power. We take into account the changes in the demand. As I said, we assume that there is a typical day in which we have different scenarios of demand, and we have also different scenarios of luminosity. These scenarios are taken into account in the charging of the battery. And we also have a detailed energy operation that is included in the model. So we include in the model not just the part, let's say, the ITC part, so that you have to have the ITC demand has to be satisfied, but also the energy conservation in time, how this works in the model. It's a humongous model. It's a huge model. So there is a paper that we are finishing about it, so you'll have the opportunity to read it, but it's just too large to be able to present it here. But I can present the ideas of what there is. So in the classical planning and in the solar, so there are some steps that are the same. So we assume that the operator already has a network of macro base stations. Like in the case, you have a network of 4G macro base stations, you want to add 5G. There are potential sites that are identified to locate the new base stations. And you can have pico or micro base stations that must be bought to satisfy the new demand, we consider a horizon of 10 years. In the classical setting, there is no solar equipment, only the capex is optimized, and the problem is to decide where to locate the base station, what type of base station should be used to satisfy the demand over the years. In the solar case, some base stations may be solar. We consider a trade-off between the planning and the operation, where, like we did before, but now it's much richer. Because with 5G equipment, we have the opportunity not just to do the cell on-off operation, but we can also do cell zooming, which is the cell can increase the coverage or reduce the coverage, and we have a dynamic reallocation of the demand. Everything is considered in the moment. And the problem provides the type and the location of the base station over the year, plus the optimal scheduling of operating features in this typical day of the year. What we found? Well, we found that current solar prices are too expensive. They are just too expensive for the market to choose solar by itself. And so we started, we did a bunch of optimization, you know, settings and so on. And we were never able, with normal prices, current normal prices of energy and solars and so on, to make the system choose solar base stations. So we started with say, okay, let's increase the carbon tax. So we started with a carbon tax and we increased the carbon tax. It was not until we increased the carbon tax 4 times for a very small network, so I'm going to show you the very small network, that we were able to have in the planning, in the optimal planning, to have a green base station. Okay, so this is the network evolution. This is the year 0 with the carbon tax of $50. And here you have the potential sites for the base stations. And this is a non-solar micro base station. And this is a macro base station. This is a non-solar micro base station, sorry. And this is a macro base station for the year 0. And then you have this evolution. And this is in year 3 that we are able to have this green base station. And then we go year 4 and so on. So you can see the changes. Of course, the demand increases over the years as well. Okay, so this is what I wanted to tell you in terms of the 3 challenges: the performance, the reliability, and the sustainability challenge. And well, now the conclusions. Well, 5G is complex. It's a very complex technology that brings a great deal of challenges and important trade-off. And we show just a few issues with respect to performance, reliability, and sustainability that just show you how huge is the market for solving those problems. And well, 5G is such a fascinating technology that let us, like Steve Jobs said, stay hungry and stay foolish in research. And many thanks to my wonderful students and co-authors that have worked on the problems that I presented today, and to the wonderful PIOT project interns that are the ones that are creating the front end of the simulation application. Well, thank you very much.